welcome back to Femboy Mathematics. So today's gonna be an extras video. I originally wanted to talk about the derivative, but my camera kept cutting, and I'm gonna have to move the recording date to another time because I'm a very busy person at the moment. I don't know if you guys can see me here. Hello. I don't know if you guys can see me because the phone's a bit low right now, and yes, I'm gonna be discussing in my drawer. It's not the ideal place to discuss things, but it works. It just works. So I'm gonna be sitting on my bed here while I discuss with you guys what I'm gonna be discussing today. So I'm sorry that this video is not about it's not gonna be about statistics and probability, or it's gonna be a continuation of calculus. Um, but today we're gonna be talking about a very important notion in topology. So this notion is really intuitive. It really is, but there's a lot of formalism behind it that I can't sort of talk about with you guys right now because it requires a lot of setting up. Like, I have to go through the rigorous notion of what a topological space is, what a topology is, not the name of the subject, but the topology, as in the object itself. I also have to get into continuous functions and stuff like that, and homeomorphisms. In fact, I'm just gonna give you guys. I gave you guys already an overview of what a homeomorphism is, but in this case here, I'm gonna be skimming over 9 or 6 lectures worth of, notes, or worth of words of topics, in order to give you guys a good picture of what this important thing is. So, in today's lecture, I'm going to be talking about something called manifolds. If I can find my freaking marker. They were talking about manifolds. And no, to the engineering students out there, I'm not talking about the pipe fitting that connects one pipe into more than several pipes. No, I'm not talking about that kind of manifold. What I mean by a manifold is this is a topological space, or it's a space that locally resembles Euclidean space. Okay, so what do I mean by that? So first, what do I mean by Euclidean space? So Euclidean space is what you guys intuitively know to be flat space, or as Femboy physics would put it, Minkowskian space. Just flat, unchanging space. The usual x-y axis you guys see in your everyday math life is an example of something we call R2, or two-dimensional Euclidean space. It's not curvy or stuff like that. It's just two perpendicular axes, or as we put it in terms of linear algebra, two orthonormal bases. Or so it's a vector space of two orthonormal bases. Okay. Or less sophisticated language, orthogonal bases, or perpendicular bases. And as I stated, once you know your basis vectors, in my linear algebras episode, once you know your basis vectors, you know what every other vector in your space looks like. So in this case, it would not be curved vectors, but straight vectors, of course. So that's an example. This is an example of a manifold. Actually, this is an example. I mean, it's not really a manifold in the sense that we defined it, but it's a topological space nonetheless. And this is what we're going to be defining, or this is the bedrock for what we're going to call manifolds later. So it's a bedrock for the definition of a manifold. So I don't know if I did this lecture here or in my Professor Femi channel, but I'm pretty sure that maybe some of you already know the notion of what a map is. So if I have two sets, AB, a map is a association of elements from A to B, to elements in B. And okay, a homeomorphism now, formally speaking, is a map between two topological spaces, something like R2 or Rn, such that it is continuous and bijective. So, alright, so now I need to define what continuity is. So, in calculus, I I talked about continuity in my limits videos, and continuity is basically like, okay, I can draw a curve without lifting the marker. So this is an example of a discontinuous curve. So here's like the big brother definition of what a continuous map is. So a map between two topological spaces is considered continuous when its pre-image is open in the original space and its image is open in the domain. So given a map F from two topological spaces A and B, so I'm not thinking of A and B as sets anymore but just topological spaces, F is continuous if and only if the image of F is open in B and the pre-image of F is open in A. Or really, what you guys want to think about it is, let's say I want to place a curve on the surface of a sphere. Okay, so I have a map. So I have a line and then I have a sphere, and then I want to sort of embed this onto the surface. So let's say this is F. It's continuous when if I draw a circle along the surface of the sphere, no matter how small or how big I shrink that circle, or something we call an end ball. This one here is just a regular circle, really. When I close in that circle, it doesn't get stuck. So let's say I have a discontinuous map of this line to this sphere. If I take this circle over here and try to shrink it, it's gonna get stuck at this part here, at this region where discontinuity lies. So I can't shrink the ball, and that's what I mean by F is not continuous. And it's continuous when essentially things are held together. Okay, and what I mean by bijective is that it's a one-to-one association. So no matter here is lost, and likewise when I remove this from the circle, right? So if I want to instead map the circle onto the line, so instead of putting the marker into my hands, I'm putting my hands into the marker. Nothing breaks on this sphere. So if I end up punching a hole when I try to put the sphere onto the line, it's not a homeomorphism. But it is a homeomorphism when I can put this onto the circle without breaking it, this line, and I can put the circle on the sphere onto the circle without breaking the sphere. That's an example, or a very intuitive explanation of what a continuous map is, or a continuous map, a continuous bijective map. But that's not to say that this is a homeomorphism between this sphere and this over here, because homeomorphism is a continuous bijective map between two like spaces, and this is not bijective, for Christ's sakes, because if I try to map every element here onto stuff here, so every point on this line, it only occupies a line on the sphere. It doesn't get mapped to every point on the sphere. So it's obvious it's not one-to-one. So this is not a homeomorphism. However, if I have now in topology, I said that shrinking and stuff doesn't matter. Okay, so let's say I have a cube and I have a sphere, and I define a map such that, intuitively speaking, I'm rounding out the corners of this cube. That's my map. I'm rounding out the corners so that it looks like the sphere. Now the reason that this map, and the inverse map wherein I make edges and corners on this circle to make it look like a cube. The reason why that is a homeomorphism is because every element here on this, or every point on this cube, gets mapped to at least one point on the circle. And likewise, every point here in the circle gets mapped at least onto one point here. So there are no points on this, there are no two or more points on the circle that get mapped onto one point on the cube. And likewise. So it can only be a one-to-one association between these two. And likewise, when I apply the function or the map, the continuous map, the reason why it's continuous is because I don't break the cube in order to make a circle. And likewise, I don't break the circle to make a cube. And this works the same way with the coffee and donut analogy. I can mold the cup outwards, and there's the little pit inside where you pour your coffee in, and you may be thinking, oh, maybe that's a hole, and maybe stretching it out is considered not continuous because you're removing a hole. Well, it's not really a hole to begin with. So it's still continuous, it's still one-to-one, even though the donut is significantly smaller than the mug. What I can do with topology is I can just enlarge it. Right? I can blow it up and then make it such that the matter between the two are precisely the same. Or at least the volumes of both of them match up. Okay? It's just that when I want to turn a circle into, let's say, a donut, so I want to turn a basketball into a donut. So I have a basketball, which is essentially just a sphere, right? I mean, it really is a sphere. It's essentially a balloon with gas inside. So it's a hollow thing. Don't mind the gas inside. That's not part of the space. And okay, let's say I want to turn into a donut. Well, okay, yeah, I'm gonna punch two holes into this sphere, and I'm gonna bring those two holes and sew them up. Well, now you have a donut. But the thing is, that is not a homeomorphism, because I need to punch a hole into this and sew those two holes together to get a donut. And likewise, here in a donut, I need to break the stitches. I need to cut along some axis here and then patch things up to make a basketball, which is, one, it's not allowed in topology, and two, that is not a one-to-one relation. Even if I try to somehow make this such that, I try to make this such that it has the same volume or matter as the donut, when I try to mold it into a donut, I can't really turn it into a donut without having to punch two holes in it. And punching holes is a no-no. So therefore, not a homeomorphism. So a direct map from this to this is not a homeomorphism because it's not continuous. It could be bijective, of course, but it's not continuous because I have to punch a hole into this to get this. And likewise, I have to punch a line through this and patch things up to get this. So that's like my overview of homeomorphism. So now let's get to the main topic. What is a manifold? So a manifold, formally speaking, is a topological space that is locally homeomorphic to Rn. So what I mean by this, intuitively speaking, is that when I zoom in on the surface of the manifold, it looks flat. It looks like, it's like the surface of the Earth. That's like one of the most prominent analogies of what a manifold is. The surface of the Earth. Alright, or just a regular sphere. A sphere is an example of a manifold. So S2. We call it S2. So this is a sphere. Although it looks curved out here, if I zoom in on the surface, on like a small patch of land here, it looks flat. And that's what matters when it comes to a topological space being a manifold. Now, it can also be homeomorphic or locally homeomorphic to R3, which is three-dimensional Euclidean space. You know, the x, y, and z axis, and all the numbers that you can construct from them by adding their coordinates up, or linear combinations of them up. The ball, B3, so it's essentially a sphere, but it's hollowed out. It's filled up with matter or points. So B3. This is an example of another manifold because it is locally homeomorphic to R3 or three-dimensional space. If I go inside the ball and I'm looking around inside the ball and then there's matter all around me. If I take a small patch of it, any kind of patch, and I try to map it to regular non-curved three-dimensional space, nothing happens actually. It's just that it gets exactly mapped onto that stuff. I can find a homeomorphism, right? I can find a homeomorphism such that, or a map such that it is a homeomorphism between that small patch I took and my three-dimensional Euclidean space. Okay. So, you guys learned about dimensions back in, of course, in high school and elementary. Zeroth dimension is just a point. The first dimension is just a line. The second dimension is a plane, and the third dimension is space. I have length, width, height. But when in topology we talk about dimensions very differently, especially with manifolds. Namely, the dimension of a manifold, intuitively speaking, is precisely basically the dimension of what space it is locally homeomorphic to. So that Rn, that n in Rn that I was saying a while ago, that is the dimension of your manifold, or at least the topological dimension of your manifold. So, although you may see a torus or a donut, which we call T2, as it looks 3D from out here, when we look on the surface, it looks like two-dimensional Euclidean space. Hence, we say T2, and we call this a two-dimensional manifold. Same thing with the sphere. Although it looks three-dimensional to us, geometrically speaking, topologically speaking, when we zoom in on the surface, we actually find that it is locally homeomorphic to R2. It's a flat surface. So therefore, its topological dimension would be 2. Hence why I said it's called S2. Now how about a straight line? A straight line is just one-dimensional because it is only locally homeomorphic to R1, or just another line. A line can't be homeomorphic to a plane after all, or it can't be homeomorphic to a cube, so it can only be homeomorphic to a line. Now another way of thinking about this is that, look at the line. I can only travel in one direction, or one degree of freedom, which is up or down, or left or right, front or back. Now, if I take a plane, such as the surface of a sphere, I get 2 degrees of freedom. I have up, down, left and right. So I have up, down, and left and right. So 2 dimensions. It takes 2 coordinates to describe a point here. Now for a ball, a topological ball at least, not the ball you guys intuitively think, now I have length, width, and height. So hence 3 dimensions. I have 3 degrees of freedom. Y and this X. So I have up, down, front, and this is front, back, and then left and right. So hence 3 dimensions. So there are many things you can do with a manifold because it is a topological space. You can compose two topological spaces or two manifolds together in order to make another manifold. And you can also, you can technically punch holes into manifolds so long as you sew it back up. Okay, well, this is not going to be a homeomorphism strictly speaking, but you can legally, well, legally in the sense of, in topology sense, you can legally modify a manifold, by punching holes in it, so long as you replace that hole with something, and that's something called surgery, geometric surgery. And frankly, that was like the thing I was studying recently, until I went back to abstract paintings. So yeah, actually, I really am using a lot of topology nowadays, especially with abstract paintings, and a couple more other papers that I'm working on as a hobby. So there's that. That's a small overview of what manifolds are. Now, another very like some a very high end example of what a manifold is the Kaluza-Klein manifold, or yeah, the Kaluza-Klein manifold, which is used in string theory, one of the most advanced physics theories. I would appreciate it if Femboy physics covered string theory, and its mathematical beauty. So that's one thing. I think Kaluza. No, no, no. Yeah, that's one example. I think. I guess another example would be the Klein bottle. You guys already know that. It's basically the shape with no volume, because so it would look something like this, I think. So excuse my poor attempt at trying to draw a Klein bottle, but it would look something like that. Another example is the infamous Mobius band. So a Mobius band is if I take, I'm gonna use this tissue and I'm gonna fold it up. So a Mobius band is if I have a strip and then I twist it and connect the ends together. And what's interesting about the Mobius band is that if I travel along one side, I end up on the other side. So you can think of this shape as a one-sided shape, as opposed to regular strip, which you have to cross over the boundary. So the boundary is, of course, where points can't go beyond. You can't go to the other side without crossing the boundary. But with a Mobius strip, all you have to do is travel along the surface to get to the other side without having to cross the boundary. And boundaries are another important thing to manifolds. So boundaries are basically what the what bounds the space, essentially. And to define a boundary, what I want to do is define something called a boundary point. So let's say I have a shape here, any shape you guys can think of. It's just a blob, and I have points inside. So there are three parts of a topological space: the interior, the exterior, and the boundary. So the interior it's an obvious, like, common sense definition. It's points inside the manifold, or on the manifold, or the topological space. The exterior are points outside of the manifold, although we like to think of the exterior as like some endless void that the space is living in. Now, what's special about boundaries is that they are neither inside nor outside the topological space. But what's important is that if I pick a boundary point, so a point in this manifold or this topological space is a boundary when if I draw a circle around it, and no matter how big I stretch it, or how small I shrink it, there will always be points inside the circle that are both inside and outside. So what I mean is, a point inside this manifold, or an element inside this manifold, is a boundary point if when I draw a ball around it, if it's two-dimensional, of course, I'm going to draw a sphere around it. If it's two-dimensional, like geometrically speaking, I'm gonna draw a circle around it or a disc. When I shrink that circle, there will always be interior and exterior points inside the circle. No matter how small I shrink it, no matter how big I um, grow it. And I think that's one of the most that's like one of the best definitions of a boundary mathematicians have ever made. It's both intuitive and it captures the notion of what it means to bound a space. So it's a really nice and elegant definition of what a boundary point is. So let's go back to the ball. So B3. So don't confuse this with derivative notation, okay? But we use partial to denote the boundary of a space. So what is the boundary of B3? Okay, so I have a ball. Let's say this is a ball, not just a disk. So what is the space, or topological space, or manifold that bounds B3? So essentially, if I allow the points to be like conscious beings and I give them a will to escape the ball, there's gonna be like a boundary, a place they cannot go through. So what is that space? So I'm gonna give you guys a second to think about that. And the answer is, it's the sphere. Why is it the sphere? Because no other shape can fully enclose B3 like the sphere. How about just a circle? Let's try circle. Okay, let's try circle. Let's say that a circle is the boundary of B3. Okay, so using my definition a while ago, I'm gonna pick a point inside the circle. Okay, it's not clear. Let's use a clear analogy. I'm gonna pick a point in this circle, and I'm gonna draw another circle or ball inside it. In this case, it's three-dimensional, geometrically speaking, so I'm talking about a sphere here. Okay, so there will come a point wherein I shrink it, and there will be some points that are inside. So this circle is floating inside the ball right now. All right, it's floating inside the ball. It's sitting still. Okay, if I grow it large enough, there will come a point, or there will come a time wherein it will have points that are outside the ball and inside the ball. But the thing is, when I shrink that sphere, which I claim to be centered at a boundary point, which we claim to be a circle, when I shrink it sufficiently, there will come a time wherein every point inside that sphere is inside the ball. So hence, a circle can't possibly be a boundary. So, alright, so how about T2, the torus? What is the boundary for torus? Now the funny thing is, the torus is hollow. It's like a sphere. Well, a sphere, as we know it, is a hollow thing. It is just the set of points equidistant. It's just a set of points that are at an equidistant, an equidistant measure from the center. So it's all points that have an equal distance away from a central point. That's the definition of a sphere or a circle. Now here, there's nothing inside the torus. What I'm talking about is merely the surface of a donut. So in topological language, this is constructed from two circles S1, but it's different from a filled donut, where it's S1 cross D2. Okay, so these two are different. However, if I take the boundary of S1 cross D2, which is a filled out donut, of course the boundary will be a torus. So it's surface, essentially. So if I have a topologically three-dimensional manifold, the boundary, or its boundary, is essentially a dimension lower. So what do I mean by this? So let's let's take it down a notch and let's talk about disks. So a disk is a two-dimensional version of the ball. So it's a circle, but all the points inside it are filled up. So there are points inside the circle. So this is an example of a disk. We call it D2. What is the boundary of D2? Well, D2 right now is a two-dimensional space, and I said a while ago that it's a dimension lower. So that means its boundary is one-dimensional. And in fact, it is one-dimensional. It's a circle. Because, let's say I just take a line, or just one line here. Alright. Line is a part of the boundary, of course, yeah. But it's not the full boundary. Okay? Because, how about the points over here? How about the points over here? When I shrink it, yeah, sure, but it's not defined there as well. So it's incomplete if I take just a line. Now, a sphere can't bound a disk because this is what it will look like. So I have a sphere, and then in the maybe the equator is where the disk is. That's where the disk is. But the thing is, let's say I pick a point over here. Now I'm gonna build a sphere around that point, and oh, look here. There are no points that are in the interior of D2 that are inside this ball. So it can't possibly be a boundary. Now S2 is an obvious, S1 is an obvious boundary, a circle, and it is in fact just one-dimensional, because you only have 1 degree of freedom. I can only go clockwise or counterclockwise along the circle. I can travel like this, or like that, as opposed to the disk. So there's only 1 degree freedom, and then the disk we have 2 degrees of freedom. So you guys can see now. Now how about a line? Well, it's obvious. A line is one-dimensional, so therefore it must have points as its boundary, and you're right about that. So Sn in general, a sphere is defined to be the set of all points x, y, x1 up to x sub n, all in R, such that x1 squared plus plus xn squared is equal to 1. That's the definition of a sphere. And this is why for a circle the equation is x squared plus y squared equals 1. And why for a circle and for a sphere it's x squared plus y squared plus z squared equals 1. So really a circle is it's hollow. But how about what if we have S0? That's a bit weird. Because we've defined this up to an arbitrary number n, but what if we have 0 here? We only have 1 point. Or actually, it's 2 points. So S0 is defined to be 2 points. 2 disjoint points. And in fact, the boundary of this over here, this line, is precisely S0. So if I define this to be the unit interval running from 0 to 1, its boundary is precisely 0 and 1. So the boundary of the unit interval, which you call I, is simply S0, or 2 points. And yes, this is still a manifold. Still a manifold. Unit interval, also a manifold. Torus, manifold. A ball, manifold. Disk, manifold. Circle, sphere, manifold. A sphere that is somehow like 100,000 dimensions, that requires 100,000 dimensions to describe every point in it, also a manifold, so long as it is locally, so it locally looks like flat space. Well, flat in the broadest sense of the word, or the loosest sense of the word. So this is my small video on manifolds, and again, I'm skipping over a lot of topics in this lecture, and frankly I wish I could say more, It's just that it requires a lot of um, training in pure math, and frankly, when I first studied topology, I did not know you sort of needed to learn about real analysis before getting into topology. So I started topology without actual, like, without a formal training in proving stuff, and it requires a lot of proving to learn topology. So there's that. So my notion of manifolds. And manifolds are very important because they come up in differential geometry, and differential geometry is applied in physics, in general relativity. And there's a lot of ways you can apply manifolds. Also in solving partial differential equations and stuff like that. Partial differential equations can be associated to a certain manifold because partial differential equations are used a lot in differential geometry. And in differential geometry, it's all about manifolds, but specific kinds of manifolds, because right now I'm talking about manifolds in the loosest sense of the word, or in the loosest sense of the object. But there is a way to differentiate two manifolds from each other without them, despite them being homeomorphic according to our definition a while ago. So although I can mold them together, I can make them distinguish from each other with something called a metric. But that's for another video. So again, I'm sorry that I'm not able to make or crank out these new videos, and I only have time to record this one extras video that you guys probably don't want. But new videos are coming up. I'm thinking about them. I'm thinking of ways on how to sort of make them easier to digest. And I don't know if this lecture was even digestible for you guys, but I hope you guys enjoyed it. And that's it for this lecture. And I'll be see you guys. So, bye bye.